So we're continuing chapter 10, where we're talking about vibrations in continuous systems. And in this section, we're going to talk about axial vibrations in a uniform bar. So if we consider a uniform bar, as shown in the figure here, which has a length of L, a cross-sectional area of A, and a density in terms of mass per unit volume, rho. So we can let U of x and t be the axial deformation of the material at point x in the equilibrium position. So you see we've got this material at some distant point x with some length dx, and it is deformed in the deformed configuration, and U of x and t describes this deformation. So the free body diagram, mass acceleration diagram of this infinitesimal element of the bar is shown here. So from the free body diagram, we have the force given by the stress, sigma of x, multiplied by the area A. And on the other side, sigma of x plus dx, multiplied by the area A, where dx is the length of the element. And then for the mass acceleration diagram, we have our mass, which is the density, times A times dx. So this A dx is equal to the volume. So that basically gives us the mass times the acceleration d2u by dt squared, which is the acceleration in the horizontal direction. So we can apply Newton's laws and say that the sum of F equals ma. We've got sigma of x plus dx times a minus sigma of xa is equal to rho a dx partial to u by partial t squared. And we can cancel out the a's in each of these to see that we've got, so basically we have sigma of x plus dx minus sigma of x is equal to rho dx partial to u by partial t squared. Now for a linear elastic material, sigma, the stress is given by, is related to the strain through the Young's modulus. So sigma is equal to E epsilon, where E is the Young's modulus and epsilon is the axial strain, which is equal to partial u by partial x. For small deformations, we can approximate sigma of x is equal to E partial u by partial x, and sigma of x plus dx is equal to E partial u by partial x plus partial to u by partial x squared dx. So our equation of motion then becomes E partial u by partial x plus partial to u by partial x squared dx, which is just our sigma of x plus dx, minus E partial u by partial x, which again was just our sigma x, is equal to rho dx partial to u by partial t squared. We can cancel out this E partial u by partial x terms, and we get that E partial to u by partial x squared dx is equal to rho dx times partial to u partial t squared. We can cancel out the dx's and simplify this to partial to u by partial x squared is equal to 1 over c squared partial to u by partial t squared. Where here, again, this is the wave equation, similar to what we saw for the transverse vibrations in a cable. Except here, the wave speed c is equal to the square root of E over rho. So just like for the cable example, we assume a solution of the form U of x and t is equal to U of x times t of t. So we're again using the separation of variables technique. And we substituted this into the equation of motion and proceed as we did before. We can find that U of x is equal to a hat sine px over c plus b hat cosine px over c. And t of t is equal to c hat sine pt plus d hat cosine pt. So the total solution becomes a sine px over c plus b hat cosine px over c, which is the mode shape, which is only a function of x, multiplied by c hat sine pt plus d hat cosine pt, which is the harmonic motion, which is only a function of t. Again, the constants a and b are determined from the boundary conditions, and the constants c and d come from the initial conditions. So some common boundary conditions and responses for axial beam configurations are shown here. So we could have a fixed free, so at the fixed end u is equal to 0, and at the free end partial x by partial u is equal to 0. A free condition would have partial u by partial x equal to 0 on both ends, and fixed would have u equals 0 on both ends. So here we can see for each of these boundary conditions, what is the frequency equation or this characteristic equation that describes the natural frequencies, and then what do we get for our natural frequencies in terms of Pn, and the associated mode shapes Un.